x86-64 also provides some SIMD instructions to work on floating point numbers. And SIMD means single instruction, multiple data. So these are like the add-s and sub-s operators that we saw before, but the ones with a p, they multiply more than one pair of numbers together or add more than one pair of numbers. It turns out that these registers that hold floating point numbers are actually 128 bits wide, not just 64 bits wide. And so add PD takes the bits in that register and considers the top half of them to be one floating point number and the bottom half to be another floating point number. And the same for XMM1, and it performs two additions at the same time, two independent additions working on the pairs, which are the top halves of the registers and the bottom halves of the registers. Since those registers are 128 bits wide, they can hold four floats, four single precision numbers. So mul PS means a parallel multiplication of single precision numbers. So there are four of them that are pairwise multiplied, and the results are all put into XMM1. So the low 32 bits are one result, the next 32 bits are the next result, and so on. To get a compiler to use those SIMD operations is a little bit trickier than getting it to use other kinds of floating point operations. For example, this looks like a good candidate here. We've got four sets of numbers that need to be multiplied together. Right, so we would like to use a mul-p operation to do these first two multiplications at the same time and the second two multiplications at the same time. Written as this, GCC will not use the mul-p operator, however, because there are a lot of constraints on it. In particular, it won't work right if A and B both point to the same memory, and it also won't work right if A and B are not 16-byte aligned. Whereas most of x86-64 doesn't require an alignment, mul-p does. So to get the compiler to actually use the vector versions of the numbers, the operations, the parallel versions of the operations, we have to give it a lot of hints. We can say, with restrict, we promise not to pass in aliasing addresses here. We promise that they'll point to different memory regions. And you can also assume that these will be 16-byte aligned. So with those assumptions, no aliasing and no 16-byte alignment, then GCC-03, which is what's needed for it to figure out how to use these parallel operators, will generate code like this. RDI is going to be the pointer corresponding to AI, so we're going to move in two chunks. We have four floating point doubles, so the first two, actually the second two here, fit into XMM0, and the first two are put in XMM1. And then we multiply the second two of BI against the second two of A, and the first two of BI against the first two of A. The punchline here is that there's only two multiplication instructions, not four multiplication instructions, but all four results are created. Then we move them back into A as the result.